kind introduction. Yeah, so this SRM is in Chennai. I think the flyer had Bangalore. No problem. So yeah, thank you very much. Okay, I'll get started. I'll just stop the video so that it doesn't affect the procedure.
Yeah, we'll welcome Dr. Jay Kumar also. Dr. Jay Kumar Vaidya also joined. Thank you, sir. Thank you for joining.
Thank you, sir. Thank you.
Let me just.
Thank you, sir.
Okay. Hi, sir. I think is my screen visible?
Yes, sir. Variational principle to variational embodiment. Yes, sir.
Yes, sir. Thank you. So I'll just push. Yeah. Okay. Thank you. Okay. Thanks, Dr. Emmanuel, sir, for a kind introduction, and MNIT for the opportunity to speak with the participants, and also I thank Dr. JB for this opportunity again. Okay, as I had mentioned, my background is in computational quantum chemistry, and I have done works in what is called density functional theory and ab initio electronic structure theory for excited state characterization of molecules that is used in solar cells. I've also used quantum algorithms and machine learning for understanding these properties as well. So, yeah. I would like to start with so the topic that was given to me was variational algorithm. So the idea is to uh, build the variational theorem. Discuss the variational theorem that stands as the motivation for developing variational algorithm in the within the quantum regime. But even before getting into quantum, I would like to discuss some the application of variational theorem in classical way of doing things as well, because it's been the engine for various computational practices within, especially in quantum computational chemistry. So so this way it will open up the idea of variational algorithm, that it is not only related to quantum computing, but it stems from the fact of variational theorem, and it's been borrowed in classical way of doing things, computational chemistry especially, and also quantum computing also embraces it. So then briefly introduce fault tolerant quantum algorithm, and then therefore we talk about NISC then from there, and VQE, the specific variant of variational quantum algorithm, we'll discuss. And I would like to emphasize the idea of expectation value in this talk. So I'll get started now. Please feel free to just drop. If you have any questions, please feel free to engage. So, okay, as you all know, it is known to many of the people, but I'll just anyway start off with the very fundamentals. So the dynamics or the mechanics of microscopic objects is governed by Schrodinger equation. There are two variants of to Schrodinger equation. One is time independent and time dependent, and this one is what we see in most of the time is time independent non-relativistic Schrodinger equation, where the H Hamiltonian operator within the quantum mechanical language acts on the wave function, which describes the state of system, carries the information about lots of information about the system, and then it's an eigenvalue equation. Therefore, on the right hand side we have the associated eigenenergy and the eigenvector or eigenfunction. So the Hamiltonian operator usually corresponds to the total energy of the system within in computational physics chemistry, and then psi is the wave function that represents the state of the system. This is the starting point for understanding Schrodinger, variational algorithm. So it all begins here. So now as I mentioned, this is a eigenvalue equation, and which means the idea is to extract the eigenvalues and eigenstates or eigenfunctions or eigenvectors of the associated operator. Usually it's Hamiltonian operator, but there are other quantum mechanical operators that can be applied as well. So it's all about finding eigenvalues and eigenstates within this quantum chemistry approach. So the ground state, and most importantly, it all starts with what is called ground state energy, or the lowest energy that the system can possibly exist in, and that is therefore is central to quantum chemistry. This leads to efficient calculation of various other properties that may not be necessarily in the ground state, such as reaction rates, binding strength, etc., which are can be derived or calculated with reference to the ground state. Therefore, the ground state energy, the knowledge of the ground state energy, is central to the idea of practical quantum chemistry. And then usually the Hamiltonian is the sum of the, in general, kinetic energy and potential energy. So that T is the kinetic energy and V is the potential energy. Okay, I just want to paint a picture here. What could it mean? So we have a helium atom. There is a nucleus at the center, and there is two electrons around it. So this non-relativistic Hamiltonian has these terms, where this is the kinetic energy of the first electron, second electron in this del operator, and then we have the electron repulsion with the first repulsion of the first electron with the nucleus, repulsion of the second electron with the nucleus, and then the electron attraction term here. So this is how we build the Hamiltonian within the quantum chemistry regime and non-relativistic regime again. So the R1 and R2 are the distances of how far these electrons are away from each other, and also from the nucleus. So for helium atom, the number of electrons is 2, the nuclear charge is 2. So it all begins here, and we would like to apply this, substitute this Hamiltonian into the time independent Schrodinger equation, and therefore calculate the eigen energies and eigen values. Solving the Schrodinger equation exactly for the helium atom is just not possible because of the problem. It's usually called the many body problem, or this two body problem. Therefore, this is just a second. This is a hindrance to obtaining the exact result for uh, this kind of integral differential equations in quantum chemistry. So therefore, approximations have to be called for, and there are various approximations. One such approximation is the variational method, and variational method are widely applied in classical and quantum mechanics and is closely related. It is, in fact, it's an idea from the way calculus of variation for mathematicians out there. So originally proposed by a little bit of history, so that there is some connection with the principle. So proposed in 1873 by Lord Rayleigh, and the present version is called the Rayleigh-Ritz approximation or variational principle. The idea is the ground state has the lowest possible energy. Naturally, we can vary a test wave function. We can design a wave function, by having a knowledge of the system. So then minimize the wave function based on some parameters, minimizing, which means we can minimize the energy guided by the metric energy as a metric, to get a good estimate of the ground state energy. And the scheme is as follows. The statement is that for a given Hamiltonian H and any normalized trial wave function, we start off with the trial wave function. That's the guess wave function that we can come up with. It can be an educated guess, and it has to be normalized going by the principles of postulates of quantum mechanics. And then the expectation value of the Hamiltonian provides an upper bound to the true ground state energy. So that there is something called true ground state energy, which is E naught, and the energy that we obtain by solving the Schrodinger equation will always be higher than this true ground state energy. And this is the statement of the variational principle. So therefore, we can use this to develop an algorithm that can help us identify or calculate the energy associated with the wave function. So by tweaking this trial into better and better form, we'll be able to find the get much closer to the E naught. And so it has several applications. In fact, this is like the workhorse for various other this is kind of subroutine for various algorithms, especially the Feynman's path integral is deeply rooted in variational principles. Hartree-Fock method used to approximate wave function is a variational approach, and then also quantum many-body systems, multi-electrons and molecules that needs to be studied, which cannot be solved exactly. All resort to this variational principle, and the algorithm thus born from there. So variational theorem based algorithm, this is the step. Gives a good trial wave function, come up with get psi, which is as good as it can get, like the original ground state wave function. We do not know what exactly it could be, but however, we'll start off with a educated guess. The educated guess can be low, medium, and high, and even higher. So that determines kind of various hierarchies within computational chemistry. So now to calculate the expectation value, this is one of the important things, because this is where the statistical picture comes into the play. And we have a operator that we want to observable, that we want to understand or extract information of, and we sandwich that between the wave function that we have, and that is divided by the inner product of the same wave function. So this is a kind of an average picture, and this is usually called expectation value of an observable. So this gives us an upper bound, again, as stated by the variational principle. So this energy thus obtained will always be greater than the true ground state energy. And now vary your guess to minimize the upper bound and get as close as possible to the true ground state energy E naught. So the important thing here to note is that, as usual, the first guess, as I said, educated guess is very crucial, because the poor guess can lead to very, it's far off from the E naught, while a good one can come much closer to E naught. So that is the idea about this thing, variational algorithm. So what are its offerings? Basically, a very important thing to note down is provides a variational framework. There is a framework with which we can approximate the ground state energies using trial wave function. The idea of using the trial wave function can be yeah, invoked within this variational algorithm, and there is a guarantee of the upper bound. So there is no way that this wave function, the energy corresponding to the wave function, can go below the true E naught. This is the green line, and indicates the true E naught, and it is never possible to go below that, which is guaranteed by the variational theorem. Therefore, we can half of the problem is solved. The problem now is to find a place here, a position here, which is very good in agreement with the experimental values, let us say. So the idea is, I mean, as you can see, I'm trying to here, I'm trying here to appreciate the idea of the variational theorem, and therefore the algorithm, that the half of the problem is solved, that we do not have to look for this search space at all. We can just simply ignore it. It doesn't even come into the picture. However, we can tweak the wave function, parameterize the wave function, and change it. Therefore, it is spanning the other side of the E naught. And again, this way, this framework again provides for various allows tailored ansatz. Usually ansatz is a term that is given for the guess wave function, or the real wave function that we want to work with, and it can be obtained from various physical intuition. The best examples are slated determinants, CA expansions, CA configuration interaction expansions within computational quantum chemistry. This is domain specific, but I just want to put it out anyway. Again, another domain specific thing is underpins Hartree-Fock, MCI, MCSCF. All these wave function based methods are again variationally solved. So what this variational framework is offering is like huge way of very big, very good scope for doing lots of computational chemistry. And then, of course, mathematical stability, energy minimization ensures convergence. There is always uh, the convergence is always going to happen. Maybe it is not global, but the convergence will happen. So reaching the global minimum is up to the way we handle the wave function. However, the minimum will be reached. So that's the offering from the variational algorithm. So all these ideas will be carried to in the quantum setting also. So what are the challenges that we usually come across in variational algorithm? So the poor choices, if the initial wave function is not good enough, it will lead to inaccurate energies really far off from the real energy. So that's the problem there. And then more accurate variational forms, if I were to, as I mentioned, the hierarchy, the way I can parameterize this psi, and I can make it better and better, then there will be lots of parameters which scale exponentially with system size. So this kind of variational framework throws some challenge, which is exponential in nature because of the number of parameters to be handled. And then variational optimization may get trapped in local minima, as mentioned earlier. So there needs to be a way to come out of it. And then again, another domain specific. Other the electron correlation and basis set sensitivity, these are kind of domain specific in computational chemistry, so this can be a problem while using variational framework. Okay, so what is the component? Now that we have seen the variational theorem, and we have slightly developed the idea of variational algorithm. What could be the components involved to develop this algorithm? The first thing that is important is, I mean, the first thing that would be required according to the Schrodinger equation is the Hamiltonian. The Hamiltonian is given to us anyway, so it comes from the knowledge of the system. It can be coming. I mean, usually it is computational physics, chemistry, Hamiltonian, but in quantum setting, it can come from anywhere. So the must be normalizable, and the wave function has to be normalizable. Again, these are the constraints imposed by the postulates in quantum mechanics. And then another important criteria is basis set, which is again domain specific. The trial wave function is expanded in finite basis, such as Slater type orbitals or Gaussian type orbitals, and this will also determine the accuracy of the uh, accuracy of the algorithm. So the energy estimation tool, another component is the energy and estimation tool. The expectation value provides an estimate of systems energy that we are working with. It enables practical computation without solving the full Schrodinger equation. So the idea is that by solving this equation, we'll be able to calculate the expectation value, and this expectation value determines the we expect to the variational algorithm with variational framework, we expect to tweak this this energy by changing the parameters of the associated wave function. So the optimization procedure is important here. So the optimizer can be gradient based or non-gradient based. Widely used are gradient descent, Newton-Raphson, and conjugate gradient based. So these are the basic components that is part of the variational algorithm. That already only in classical setting. So what are the criteria? What are the criteria involved? The major criteria is two. Again, first thing is parameter. This parameter needs to be tweaked, optimized properly, so that we reach the convergence. Therefore comes the convergence criteria. The energy difference between the iteration is below a chosen threshold. We need to hit some accuracy. In fact, in quantum chemistry, the accuracy is milli-Hartree in regime, so 0.00013 Hartree, and that needs to be hit in order for the procedure to exit, the algorithm to exit. So these are the criteria that we'll look out for while writing the algorithm here. Okay, so before going to quantum algorithms, I just want to take a pause here and see if there are any questions here, because this will form the foundation for the upcoming quantum based variational algorithm. Okay, if there are no questions, I'll just move on. So quantum algorithms. Okay, now we'll discuss about the quantum algorithms. So with that, I mean, I think this audience needs no introduction to quantum computing, quantum algorithms, etc. So I'm already jumping into the quantum algorithms here. Quantum algorithms such as Shor's prime factorization, Deutsch-Jozua algorithm, Grover search algorithm, or pure quantum algorithms. Uh, They are full quantum algorithms. They operate under the assumption that the qubits are robust. There is no need to take care of the error correction and error mitigation is already taken care of. Therefore, do not incorporate any error mitigation techniques. Such algorithms are usually known as fault tolerant quantum computing algorithms and are dependent on error correcting codes. Without that, the results would be away from the desired ones. An example of error correction is surface codes. I'm not an expert in the error correction, but these are the surface codes is one of the famous error correction code. And so here it says the logical qubits, that is the one required uh, to the logical qubits is the error corrected qubits. In order to get a few logical qubits, we'll require millions of qubits. And as you already know that these qubits, the availability of the millions of qubits is really far away from today's present day quantum computer, which is far from present day reality. So now that we have discussed this full quantum algorithm, what I want to emphasize here is, since we are going to discuss about the variational algorithm, it is important to note variational algorithm calculates expectation value. So the one of the full quantum algorithm or fault tolerant quantum algorithm, the recommendation in fault tolerant regime is quantum phase estimation, which is again a pure quantum algorithm introduced by QT in 1995. It's one of the subroutines in Shor's algorithm, Hamiltonian simulation, etc., and many algorithms. So QPE is one of the subroutines there. So the QP method can be used to determine the eigenvalues of unitary operator. So let us say this is a, we all know that unitary operator is a necessary criteria to evolve a quantum state. So there's a unitary operator and this is this wave function. And then okay, I think I'll try to keep it slow. Just please check. Yeah. So the quantum phase estimation is one of the is a recommendation in the fault tolerant regime for calculating the expectation value or the energy of a system. So now this is the equation for the QPE. The unitary operator acts on the wave function psi and it yields it just yields since uh, the operator being unitary and psi k being its eigenstate, the right hand side carries the phase, pure phase on the right hand side, which is given by e to the power 2 pi I theta k and the eigenvalue psi k. So theta k is a phase corresponding to kth eigenstate. Therefore, there is n eigenstate, and this is one of that eigenstate. The Hamiltonian H is typically encoded in U via unitary time evolution operator. So how do we obtain the value for ut that is governed by that can be obtained using exponentiating the Hamiltonian at hand. Hamiltonian, as I said earlier, again is obtained using the uh, it's system specific. It's given to us. Any problem that we are going to address will have a will have already designed the Hamiltonian. So if H has eigenvalues ek, then U has eigenvalues e power e raised to I ekt, which is the phase again. And then QP extracts these eigenphases from which the energies ek can be recovered. So this is the whole idea of QPE. However, again, as I mentioned, this is a fault tolerant quantum algorithm and this requires enormous number of qubits and gates. So the standard QP circuit is shown on the right hand side. It also takes QFT, quantum Fourier transform, as its subroutine, also inverse quantum Fourier transform. And then the upper m ancilla qubits measured to eigenphase. This is the number of qubits determine the number of the precision of the calculation, and the psi is the state that we input here. So this is basically the QFT QPE circuit. Okay, now some comparison. What's the problem? The number of qubits in what's the problem with QPE is that the number of qubits in a circuit known is the width and or spatial complexity, and while the number of sequential gates define the circuit depth or like time complexity, let us say. So what is the problem then? The number of qubits required is n plus t qubits with the t ancilla qubits. So it depends on the precision that we want, and also the n varies exponentially. So here it takes only n qubits. This is a class comparison of the upcoming variational quantum algorithm, but I thought I already will put here and just motivate the necessity for variational quantum eigensolver. Okay, then circuit depth, as I mentioned here, is the time complexity. It's relatively shallow and it depends on ansatz. It's extremely deep due to control unitaries and QFT. There is series of control unitaries gates which make the QPE very, very deep. And the optimization, there is a optimization routine required here. There is no need of optimization here, which is a very good advantage, which is why this is a recommended in quant tolerant quantum regime. And then the initial state need can be flexible here, as we discussed earlier. It can be parameterized. And then here another catch here is it should have a high overlap with the target state. Okay, and then this is highly susceptible to noise, and this is high and this is moderately susceptible to noise and short circuits, which means there is less error accumulation. Here, high long coherence times is needed, therefore high error accumulation. So there is a problem with QP, which is in general any kind of problem with fault tolerant quantum algorithm. Okay, so now this VQE is what we are going to see later. But before that, I just want to paint a picture of what is the problem with QPE, and the limitations can be seen from two perspectives. One of the perspective is that it's the lack of the lack of lack of robust quantum computer with us, which means if we have very advanced quantum computer, then QPE shouldn't be a problem, which is exactly why it's a fault tolerant quantum computer also, computing algorithm also. So what could be the near-term limitations or NISQ limitations? It's the number of qubits n plus t, and the circuit is very deep, and 2 qubit gates are enormous in number, and it requires high coherence time. All these things are active area of research in NISQ eras. Therefore, it's a near-term limitation already. What about the limitation from the QP perspective? It is also one should also be aware of the uh, limitations of the procedure, right? The way we saw the limitations of variational framework in the classical setting. Similarly, the limitations of QP is due to the requirement of high degree of overlap with the ground state. Already, see, the idea is to find the ground state, energy of the ground state, and we already want to start with the energy wave function that is already much close to the ground state, which is not a requirement in VQE because it can be flexible here as stated. So there are two perspectives of the two types of limitations are near term and QP limitation. This has led to uh, people to look for different kind of algorithms. So one of them is VQE. Before going to that, I just want to paint a picture of what is the present day quantum computing. So in 2017, Professor John Preskill, he coined the term noisy intermediate scale quantum computing to denote the present era of quantum computing. So why did he have to do that? So the variational algorithms are near term high. So the algorithms that are associated with this noisy intermediate scale quantum computer are called variational algorithms, or also near term hybrid quantum classical algorithms. They are again developed based on the variational theorem of quantum mechanics. This is exactly what we saw in the classical setting. We use the variational theorem to develop some algorithm. So the intermediate scale in the NISQ refers to the number of qubits available for computation, which ranges from few hundreds to thousands. They are not millions in number. Okay, and then and also the noisy refers to the fragile nature, or you know the qubit is highly dissipative or interactive with the environment. Therefore, it is fragile and uh, the tendency to lose information, or the loss of coherence and information. So therefore, this era of NISQ demands different kind of algorithm, which is where variational theorem comes into the picture again, and then efficient error mitigation technique to extract the results which are appreciable. Okay, so now before going to the variational quantum eigensolver, which is one of the specific variant of VQE, we'll in general discuss what is VQA here. Okay, once again, variational theorem to our rescue. We invoke the idea of variational principle as a foundational tool in quantum mechanics again, and VQ is based on the Rayleigh-Ritz variational principle. Just same thing what we mentioned last time. The expectation value of the observable Hamiltonian in our case is greater than the uh, original true ground state energy. And then again we have the of theta, which is a parameterized quantum state. Okay, so E naught is the ground state energy of the Hamiltonian H. By minimizing the expectation value over theta, this theta is different from what we see in classical thing. We'll see that in a bit. But by again, it's parameterization of the wave function. This again only by tweaking the theta we'll be able to change the wave function, and by doing so we'll be able to reach the E naught as close as possible. Variational quantum eigensolver and quantum approximate optimization algorithm are two variants. QAOA has a quantum adiabatic approximation flavor to it, and their variants are the near-term algorithm, which have huge potential for demonstrating quantum advantage. Okay, so that's about VQA in general. And again, VQ is an iterative procedure. VQA works in sync with quantum simulation and classical optimization. What do we mean by that? So the classical run a shallow, we can run a shallow depth quantum circuit. I don't think we need to introduce quantum circuit here. So we have a quantum circuit which is parameterized quantum circuit. Usually it's called parameterized quantum circuit, ansatz, or variational quantum circuit. There are different names attributed given to it. And then we evolve the state from zero, get zero, vacuum state to psi zero. Psi of theta, and then by preparing the psi of theta, and then this is how it starts. And we measure the expectation value. Again, is the same thing. The only difference is, which is a huge difference. This expectation value is done on the quantum computer. However, the classical optimizer is required to tweak the theta such that E theta reaches the minimum. Okay, so the big difference between the classical and quantum computer is that the quantum computer takes care of calculating the expectation value. However, in classical way of doing things, the expectation value or matrix diagonalization is a routine, mathematical routine solved using programs in a classical setting. Application of variational quantum algorithms. So there are several applications attributed to VQAs. The most famous or widely published is finding ground state within quantum chemistry and condensed matter physics, and then dynamical simulations, of course. And then there is scope for quantum embedded quantum way of doing machine learning, which involves classifiers, regressors, and generative models, etc. And also combinatorial optimization. QA is one such algorithm which can do well in combinatorial optimization, and mathematical applications including solving systems of equations, factoring, and then principal components, which again has application in machine learning, and also the compilation and error correction. And the new frontiers that might be that might gain from the VQA is the quantum information itself and the quantum information and the metrology foundations. In fact, there is a scope for findings within the quantum physics and quantum chemistry from the ideas that can emerge from the quantum information theory. Okay, so now we'll see specifically the variational quantum eigensolver, which is a variant of quantum variation, which comes under the umbrella of variational quantum algorithm. Again, this is used to calculate the ground state energy of molecules, but it's also applied in other cases like portfolio optimization in finance, etc. So, what does it contain? Let me just go back and forth here. A quantum register is initialized in a reference state again. So this is the quantum register or quantum circuit, series of qubits, and it is initialized in a reference state, not necessarily the ket 0 state, but it can be any other state. It can be ket 0 also. But anyway, the point is that it is initiated in a state that is known to us. Okay, and quantum computer prepares a parameters quantum state and measures the expectation value. So once we have done build the quantum circuit, what happens is it calculates the expectation value. So this is the expectation. So there is a distribution associated with the quantum circuit anyway, even before calculating the expectation value, because it's a probabilistic distribution, and so there is a histogram here. And however, we want to calculate the expectation value, and therefore we subject it to the this formula, and this is done on the classical quantum computer. And then it undergoes once we have identified, this is also called cost function or objective function, and once we have extracted the information of energy, we update the theta and go back to the routine to obtain a new theta. So we try to move to gradually go to ground state again, in the variational framework, and this is how the variational quantum eigensolver works. So it involves again a quantum computer which takes care of sorry, in fact, to begin with, it's quantum register, quantum circuit, series of qubits, and then there is a quantum computer which calculates the expectation value, and there is a classical computer which optimizes the theta. So this this cycle goes until convergence criteria is met. Okay, so the quantum prepares is the same thing here, so I'll skip this. Okay, now how does it work? And the idea is that this is our energy landscape, and this is the, as you can see, the local minimum and the global minimum here. And so the cost function, which describes the which is described by the Hamiltonian. In this case, we need to emphasize that the Hamiltonian can come from, not doesn't have to necessarily come from chemistry or physics settings, but it can come from anywhere. One good example is portfolio optimization that we always come across in quantum algorithm application domain. So this Hamiltonian can come from any anywhere. The point is that the classical way of solving the objective function, the classical objective function has been converted into the Hamiltonian, because now this Hamiltonian, we can leverage the Schrodinger equation to calculate the expectation value of the Hamiltonian. So that's an important point here. That's a deviation from the classical solving any optimization using classical algorithms. With there is no need of Hamiltonian there. So this is problem specific. And then we have ansatz, what is called ansatz. Of course, we know, we've seen that it's also called parameterized quantum circuit, variational quantum circuit, etc. So this can lead to, this can point us out to the search space. So let us say this is the energy landscape that we have now, and it points out to the search space here. So I think I have to look at the, how do I look at the messages? If there is anything message chat. Okay, yeah. So thanks for that question. Actually, the local minima and global minima is an important concept in when it comes to optimization. It's again a concept within just mathematical optimization, and has application uh, across various disciplines, including physics and chemistry. So I'll tell you what the local minima is and global minima is. So let us say we have a okay, we want to solve some problem, and the problem is as follows. So there is um, there is a vegetable vendor who sells different kinds of vegetable every day, and then you want to calculate what can give the maximum profit, right? So he wants to know that. So if that can be cast as an optimization problem, and let us say there is X amount of vegetable A, there is Y amount of vegetable B, and Z amount of vegetable C, and so on and so forth. Then let us say we want to identify the appropriate values for X, Y, Z in such a way that A and B and C are sold in such a manner that his profit, which is on the right hand side of the equation, is maximized. Considering this as an optimization problem, where in this case it's a maximization problem, the maximum limit corresponds to the global minimum. Okay, although it's a maximization problem, it can be cast as a minimization problem as well, just by changing the sign. The point I'm trying to make is the maximum point can be considered as a global minimum. I just want to paint a physical picture here. And anything, it can look like a minimum, maybe, like some combination of XYZ is giving good profit than better profit than the present day or today's profit. However, it may not be the maximum, the roof we are able to hit. So that can be considered as a local minimum. So in optimization, this is okay. Now that's an analogy. Now coming back to the mathematical understanding, this is an energy landscape. So okay, another physical example that I can think of is the energy of a molecule. So the energy of the molecule can have this kind of landscape based on the interaction between them. So, and we want to calculate the native energy, let us say energy of the molecule in its native state, which is global minimum. Everything else is non-native state, because in nature, everything tends to be in its global minimum, in least energy state. So therefore, identifying this global minimum is very important in computational chemistry or physics. Okay, so that's the way of understanding energy landscape from chemistry or physics point of view, and that is where this global minimum and local minimum comes into the picture. And the other vegetable inter concept, which again, again can be cast into an optimization problem. So that there correspond the maximum profit corresponds to the global minimum. So there may be a little profit which is better than the present profit. That will still not be the local minimum. That will not be the global minimum, but will be a local minimum. Okay, I hope that answers the question. Please feel free to engage if you have any doubts. Okay, I think I'll move on to the next slide then. So now we have, okay, now this we've discussed this, and then we have, yeah, this is what we discussed now, global and local minimum. And this is our place where we want to go. It's like gravity. Imagine it to be a gravity, uh, and we do not want to lie on the table, but we want to lie on the floor. Yes, please ask, uh, Dr. Kamal Gawal. Which algorithm to have suggested for what? Okay. See, honestly, quantum algorithms are in their nascent stages. There is no one particular algorithm that we can point out. But however, the widely used algorithms are VQE and QAA and their variants. There are variants to them. They are specifically tuned for applications like in chemistry or portfolio optimization. But for beginners, we can start off with VQE and QAOA. This is again in quantum setting. I'm not talking about the classical at all here. I hope that answers your question. Okay, Hamiltonian operator. Okay, so yeah, now Hamiltonian operator is a quantum mechanical concept. Okay, it's Hamiltonian in general, quantum or classical, is the total energy of the system. Uh, it corresponds to total energy of the system. It's the way we calculate the total energy of the system. It takes care of all the energies that is possible within a system. So if we think about uh, molecules, let us say a hydrogen molecule, and there it's H2. There are two hydrogens bonded to each other, right? So there is a motion. What are the motions involved in it? The translation motion, which means the molecules will move, the atoms will move, and then there is a vibration motion, which is like the molecules will vibrate. They will shrink the bond length. They will increase the bond length, and they will also go under other kinds of motion, other kinds of change in energy state, like electronic, so on and so forth. The point I'm trying to make here is there are several facets to calculating the energy for a given system, which can be translation, vibrational, rotational, and so on and so forth. When all these are brought under one purview, that would be your Hamiltonian, and that's the Hamiltonian for which we want to calculate the energy. Okay, and in the vegetable vendor story, this Hamiltonian can be the system of the linear equation we saw, like x x times the vegetable A, y times the vegetable B, z times the vegetable C, and so forth. That can be converted into the quantum mechanical Hamiltonian. Why do we have to convert all these things into quantum mechanical Hamiltonian? That is simply because we are going to use Schrodinger equation to calculate the energy, and therefore it has to have a Hamiltonian. It has to have a ansatz or a wave function associated with it. So that's Hamiltonian. Basically, helps us to calculate the total energy associated with the system, and it can come from quantum mechanics. It can also come from anything that is non-quantum also. In for especially for the quantum algorithms we are looking at, it can come from portfolio stocks. It can be built from stock. It can be built from social networking, graph structure, kind of nodes and edges that we can build out of network. All these things can be used to build this Hamiltonian. So basically, Hamiltonian is these are some examples where the Hamiltonian can come from. Basically, Hamiltonian operator helps us to calculate the total energy associated with the system. That's about Hamiltonian. Okay, thank you. All right. Okay, I'll move on to the next thing. Okay, search space is taken care of now. Okay, now let's discuss the quantum circuits. I mean, we have seen kind of seen the essence of it so far, but how does it happen in quantum in general? So it's like walking in solution space, guided by external optimizer. Again, helps us to scan through only subset of the solution space, and we do not have to roam around the whole solution space, obviously. So this is one example of quantum circuit that is associated with variational algorithm, and this was reported in 2017 by IBM. Okay, so this is a 6-qubit circuit, as you can see, 1, 2, 3, 4, 5, 6, and they are all starting with ket 0 state. So that's the first level. Start with ket 0 state, 0th level, and then first level is the parameterized single qubit rotations, especially this one. So it can be, usually it is Hadamard gate, because this Hadamard gates helps us to put the qubits or the various qubits into superposition of states. Therefore, multiple paths are accessible, multiple states are accessible. In fact, states are accessible at the same time. Therefore, it's usually the Hadamard gate, U of theta k, and to create superposition. That's the first level. This is the first level that we are talking about. And then the second level involves entangling gates, usually C0 gate, and then parameterized single qubit gates. Again, a set of single qubit gates which are parameterized again, and this can go up to n times, 1, 2, 3, 4, like this. So what is the meaning of it? That's the depth of the quantum circuit we are talking about. So sir, kindly take 5 minutes break so that we can change the YouTube session. Okay, should I take it now? Right now, should I log off?
As per your convenience, you can take 5 minutes break.
Okay,
Three
I'll maybe restart with this. Okay, I'll not start and drop this. I'll cut and I'll cancel now, and can I go and come back right now?
Yes, sir.
Okay, thank you.